Hello everyone. Today we will continue discussing together the remaining parts in the three-phase transformer. So in the previous sessions, we analyzed the single-phase transformer, we analyzed the three single-phase transformers, and we discussed how to form the three-phase transformers from a single-phase transformer. We will continue our discussion today on three-phase transformer as a complete unit. So how to make a three-phase transformer on a single core, not by using transformer bank or single-phase transformers. Also, we will discuss the cooling of the three-phase transformer, or let's say cooling of transformers in general, okay, which is one of the important things you will see when you start working in industry. So what is the three-phase unit transformer? So a three-phase transformer can be constructed by having three primary and three secondary windings on a common magnetic core. So the idea here is we will have a common magnetic core, not three different cores. So as you can see here in this figure, guys, this is one of the shapes. So we have a magnetic core with three limbs or three arms, and every arm will be used to have the windings of one of the phases. Both primary and secondary windings of a phase are placed on the same leg or arm. So as you can see here, this is arm for phase A. This is here the primary winding of phase A. This is the secondary winding of phase A. And the same is for the other two phases. Such a transformer weighs less, costs less, and requires less space than three-phase transformer bank. Why? Because by the end you will have just a single unit. You don't have three units and connecting between them. So by the end you will have just one circuit. And also in terms of the magnetic material, it would have less magnetic materials compared to the three single phase. So if this is more beneficial, why we still need to use three single phase? So everything, guys, has advantages and disadvantages. So let's see what is the disadvantage of this one. The disadvantage is that if one phase breaks down, the whole transformer must be removed from the for repair. So this is the drawback compared to the three single phase one. You remember that for three-phase transformer bank, if we have one of the banks, or sorry, if we have one of the phases have problem, so you can remove this phase even if it is not delta-delta connection or it's not going to work as open delta. In terms of maintenance, to remove one transformer, it's less weight compared to removing the complete three-phase transformer. So this would cost less in terms of maintenance. So repair-wise, for repairing, it's going to cost less compared to the three-phase transformer. This is one thing. Another thing, as we mentioned in the open delta connection, if you have already a delta-delta transformer, you still can keep your load working at 58% of its rating. So you don't need to disconnect the transformer completely for repair. So this is one drawback in three-phase transformer core. Now, in order to understand more, guys, how can we construct a transformer? Even here, these shapes are not for a high power transformer. This could be small transformer. So how can we do that? How to construct a transformer? So in the previous slide, we could see that we need three arms. So assume that this is the core of the three arms. So we have here three arms. So how to form this shape? Actually, we agree that in order to reduce the eddy current loss, we do prefer to make our core from sheets, not from a single core, because having sheets with isolation, so this would reduce the eddy current loss. So this is one of the important things we use for all of our electromagnetic devices. So as you can see, guys, here we have two parts of our core. The first part here is in the shape of letter E. So we can say this is E shape, and this is here I shape. So we can form our transformer here from two shapes, E shape and I shape. This is one way. Another way is to have two E shapes, like this one, for instance. Here we have two E shapes, okay? And we have what's called the former. This place here, guys, we call it window. And we use this window to add our windings. How can we add the windings? Firstly, we bring this former. So this former is used to have the windings around the former here. So from this side here, we'll do the windings like that around the former. And by the end, it will be in this shape, for instance. So here we have a former, and this is primary and secondary windings on this former. And the windings will be soldered on the terminals of these formers, or terminals, as you can see here. So these terminals can be used as the terminals of our transformer. And we have a similar shape here. So this is called the former, and it's used to make the windings around it. After doing these windings, we can insert our core inside the gaps of this former. So in case of three-phase transformers, we would have now former here, and another former here, a third former here. And all formers will be inserted on the cores in order to make the three-phase transformer. Okay, so this is, guys, how can we form or construct a transformer. So we have windings, we have formers, we have magnetic sheets. All magnetic sheets are collected together in order to form a complete core. Again, these sheets have to be isolated from one side in order to make insulation in between to avoid the or to limit or reduce the eddy current loss inside the transformer. Take care, guys. The sheets have to be bunched like that here. You have here a hole in order to collect the sheets together, and then use some screws in order to avoid any air between these sheets, because if you have some air inside, this would make a very huge noise, and we can hear that actually in some transformers. So this means this transformer, because of the vibration, it can make some air gap between the laminations. So this means it needs to be more tight in order to reduce or avoid such noise in transformers. Okay. After doing that, guys, here, for instance, on this core, we have to add the insulation also on the cores like that. So we have insulating cover here. Okay. Also take care, guys, that these windings here, it's already insulated. So the wire strand itself is covered by a material like varnish, for instance, in order to be insulated. Otherwise, if it is not insulated, all the windings will be like short together. Okay, so the wire is insulated already. However, we still use another cover or insulating cover by the end here in order to make a complete isolation. One more thing, guys, if you have many voltage levels, as you can see here in this shape, can you see here you have 9 volt, you have 0 volt, another 9 volt, you have 15 volt, 0 volt, and so on. So this is the secondary side, for instance, and this is the primary side here. So in this case, guys, you may have many voltage levels. So this is also exist in power transformers, and we may have also tap. This tap can move between the windings in order to provide different voltage levels. Okay, so this is also exist in high power transformers. So here is a shape of a core type power transformer. So the core, you can see here, the core is gonna be inside, and the former along with the windings are here and covered by insulating materials. And you have also some other things here. So what are these things? Why we have some pipes like that? So we will see, guys, this in few slides. Actually, all of these transformers, guys, you know that it has core loss and copper loss. So how can we dissipate these losses? Because these losses by the end will be converted to heat. If you didn't dissipate this heat, this would be accumulated inside the transformer, and this may burn the insulation and burn the windings of the transformer itself. So we have to dissipate this heat by a way or another in order to avoid burning our devices. So we will see how to make cooling for transformer in few slides. So this is one shape of our transformer. Here, guys, in this shape, we can see a complete transformer. This is a high voltage transformer. So the transformer you can see here, it is 15 to 20 megavolt ampere. So this type of transformer is designed for these power levels, 15 to 20 MVA, megavolt ampere. And the voltage level of the primary side is 72 kV. Or sorry, guys, this is the maybe step down transformer. Yeah, so 72 to 25. So this can be in some stepping down transformers in substations. So this is 72 to 25. If I have 72 and 25, how can I recognize which side is 72 and which side is 25? This is simply can be figured out by the insulation and pushing of these transformers. So here, this pushing is insulation is higher length compared to that one. So the highest one is gonna be the higher voltages. Okay, guys. So this is, for instance, how can we figure this out? But what are all other parts of the transformer? I'm gonna just make a quick description for the other parts of the transformer here, just to let you know what do we have in reality. So it's not just terminals and winding or core. We have a lot of other functions we have in our transformer. So for instance, guys, we have here in this chamber, we have what's called on-load tap changer. So the tap changer, we mentioned that you can have different voltage levels. So tap changer is used to have variable volt from our transformer. So this is the function of using tap. So the tap is nothing but like rheostat, which is going to be slide moves on the winding to provide different voltage levels. So this is the function of the tap changer. And also we have tap changer oil level gauge. Why we have oil? Actually, oil is used in transformers for two purposes. What are the two reasons we use the transformer oil? The first reason is cooling. The second reason is to avoid any kind of spark. Because if you move a tap on windings, you expect to have some open gaps between the tap and windings, and this can make sparks. So the oil is used to distinguish this spark. Otherwise, if you have such a spark, this can make a short circuit, can make very huge fires in our transformers. So we have to use oil to distinguish any kind of sparks inside the transformer. So this is going to damp any kind of spark. Okay. Here also we have tap position indicator. So this here you have an indicator. You can see at which place is your tap right now to figure out the right position of your tap. Can you see here also, guys, unload tap changer motor controls. So the tap is not manual. It needs motor control in order to control the position of these taps. So this is also another drive system used to control the tap position. Okay. Here you can find here this arrow refers to drain and sample valves. Drain and sample valves for what? Drain for the oil. So you can get some oil samples from the transformer. So the transformer here is going to be filled with oil. And the oil again, why do we have oil? Inside the transformer itself, it's mainly for cooling. It's mainly for cooling, okay? But again, if you have, due to any reason, guys, you have some faults inside, so this is going to be damp the sparks and avoid sparks inside the transformer parts. So this is also another function of the oil inside the transformer. So we can take some samples here. Why do we need to take samples? Actually, we need to take samples to make analysis for the oil. And the analysis would provide some definite gases, and every gas will identify the types of faults that happened inside the transformer. Okay, so it's like a bit advanced topics, guys, but it's still very important topics, and a lot of research work is already done in this topic. So you can analyze the oil and see the contents of this oil in order to distinguish what is the type of fault happens in this transformer, and even expect how long life the oil is healthy right now, and expecting or predicting the lifetime of the oil. So this is due to the analysis results. So we have to get some oil samples in order to make these type of analysis. We have also what's called silica gel. Silica gel breathers, guys. So the silica gel actually is an indicator to the moisture inside the transformer oil. So the silica gel has two colors. So the color will change according to the moisture inside the transformer. So we have also the silica gel breather and indicator to refer to any kind of, if you have any kind of moisture inside the transformer oil, in order to be considered for replacing or doing some maintenance. We have control cabinet. The control cabinet is controlling all the transformer, controlling the connections, controlling the voltage levels if you would, to change something or do anything here. Also, we have here a conservator tank. So this conservator tank, guys, is filled with oil, and we have also oil level gauge here to figure out if we have any kind of leakage in the transformer oil. So as you can see, guys, it's not a simple device. It consists a lot of systems inside. And if you are going to work in this transformer, you will have a complete training on the transformer construction, the transformer subsystems, and what are the different maintenance and tests you need to do on transformers to uh, to guarantee the healthy and operation of these type of transformers. Okay, so this is one of the shapes of the high voltage transformers. Next slide. Okay, so we could see in two slides ago, we could see that we have what's called former and core. Actually, we have also two different cores for three phase. One is called core type and one is called shell type. What is the difference between core type and shell type? We will see this here in this slide. So assume that you have a single phase transformer. So this is going to be the single phase transformer in case of core and shell. So the core will have like two arms like that, and we use the windings like that, primary and secondary windings here, okay, for the single phase. And here is the three phase. And this is the shell type. So for the shell type, compared to the core type, all of cores here having identical flux. So the flux move in the core here identically. However, in the shell type, you will find that the flux is moving in the two outer arms and be collected in the central arm. So this is called shell type. In case of the three phase, here for the core type, you will have flux of the different phases moving in the different arms. Okay. But here for the shell type, you will have the flux of the phases move in the central arm and being distributed to the outer arms and come back again to the central arm. So if you would like to compare, this is here the shape of the flux. So in the core type, the flux is moving in the whole core like that. Here, the windings are distributed as high voltage in the outer side and low voltage in the inner side. So the low voltage is inside winding and the high voltage is the outside windings. And this is as well, okay, primary and secondary windings together. But here, this is a shell type. So the shell type, you still have the windings, low voltage and high voltage, but again, the flux is moving in the central arm and then distributed to the outer arms like that. Okay, so this is the shape of the magnetic flux lines in the shell type construction in case of the single phase, and this is in case of the three phase. Okay, so what is the difference? Why or what happened if we have this kind of flux distribution inside our cores? So shell type construction or shell construction is lighter than core construction. Shell construction is lighter than core construction. Three-leg shell core causes zero sequence coupling. What is the meaning of zero sequence? You know, guys, the harmonics, the zero sequence is nothing but the summation of the three phases. So if I would like to write the zero sequence in terms of third harmonic, for instance, so if I would like to get I third harmonic, it's gonna be IA plus IB plus IC divided 3. So this is called the third order. If you compare that to the neutral current of the Y connection, so you know that I neutral equals also IA plus IB plus IC, which means by the end, if you have neutral current flowing in the neutral wire, so this would be a third harmonic. Third harmonic is one of the zero sequence components. So the shell will provide zero sequence. And this is one advantage in the shell compared to the core. You have zero sequence coupling, but core can have zero sequence, and this is the difference between both. So shell construction is lighter and preferred because of the zero sequence coupling. Okay. Here we have a long comparison, guys, between the shell and core types, okay, and definitions and everything. So this is just for you to read. I'm gonna leave this for you to read. It's like 3-4 slides, okay, just to figure out the difference between shell type transformer and core type transformer, just to let you know that we have different types of cores used in three-phase transformers. Okay. Now let's jump to one important topic during the remainder time in our class, which is the transformer cooling methods. So since, guys, we have transformer losses, we have to provide a cooling technique. So the transformer, guys, is working 24/7. So we call it duty cycle is 100%. So 100% duty means it's gonna work for 24/7. It's gonna work forever. So it's designed to work forever. And you know that if you have source of heat inside any device, if you didn't dissipate this heat out, if you didn't evacuate this heat out, this would burn the transformer winding and insulation, or for any device, not only for transformers. So for any device working for 24/7, you have to dissipate this heat. You know, it's possible to have some other devices without cooling systems if it's going to be turned off for a while in order to evacuate the accumulated heat inside. So this is possible. However, this has to be designed and considered in the design phase of any project. So now, for our devices like transformer, it's going to work for 24/7. So no way to operate these devices without cooling system. So you have to have a cooling system. So what are the types of cooling systems? This is what we are going to discuss in this part right now. So we can have what's called dry type transformer. Dry type means it has no fluid inside to make cooling. So we have no fluid, just air. So this is called dry type transformers. Actually, dry type can be found for low rating transformers. So you cannot find it in like several tens or hundreds of megavolt ampere. It's impossible to find this with a dry transformer, but you can find it in several megavolt ampere transformers. Okay. So how can we have the dry type transformer? So we have two technologies. One is called AN cooling, which is air natural cooling. The other type is called AF, which is air forced cooling. Air natural means we don't have source of forced air inside the transformer. But air forced means you have something to force the air to cool the windings, like fans, for instance. Okay. We have also the oil immersed type transformers. So for the oil immersed type, you will find four different types here. We have what's called ONAN or ONAN. So ONAN is oil natural air natural. We have oil natural air forced. We have oil forced air forced, and we have oil forced water forced coolings. So these are the most well-known four types of oil immersed type transformers. So let's see, guys, the shape of these types of transformers. Here, for instance, guys, we have an air natural cooling transformer. This is ABB transformer with few kVA rating. So this is dry type self-cool transformer. In this method, the surrounding air natural circulation is used to cool the transformer. The windings of the transformer are protected against mechanical damage by sheet metal enclosure. So we have sheet metal enclosure to protect against any mechanical damage. Natural air cooling is used for a small low voltage transformer up to few kVA. Okay, guys, so it's small low voltage transformer means it's from medium to low volt, okay? But it's less or few kVA, okay? So this is a dry or air natural core. This is air forced. So for the air forced, guys, used in the dry type forced air cooling transformers, in this method, a continuous blast of filtered cooled air is forced with the help of fan through the core and windings. So you have tubes for this air, or like radiators for this air, moving with forced air to make cooling for the winding and core. This method is used for cooling the transformer up to 15 megavolt ampere. So up to 15 megavolt ampere, it's good to use air forced. Okay. And here, as you can see, this is the pushings of the medium voltage side. Okay. This is 15 megavolt ampere. Again, all of these guys are still like distribution transformers or substation transformers. This is just in distribution, by the way, so you cannot find this in substations. This is just, you can find it like close to your house or in small buildings, okay? But this one can be used in substations. What about the oil immersed one? So here is one of the oil immersed transformers. So this is the oil natural air natural. So the idea is the oil immersed transformers are enclosed in a sheet steel tank. So we have a sheet steel tank, and this sheet steel tank includes the oil inside the transformer. The heat generated in the core and windings in transformer to the oil. So once you have the transformer working, the heat will start being transferred from the winding and core to the oil. The heated oil becomes lighter and rises to the top, and the cool oil takes its place from the bottom of the transformer tank. So this is the kind of circulation that will happen in the radiators. So here we have the core and transformer. Let me just have the laser instead of the pen. Oh. So here is our core and windings inside the big tank, and the tank has these radiators here to make circulation for the oil. So since the heat is going to be transferred to the oil, the cold oil will go down and the hot oil will go to the top, and then the hot oil will be circulated inside the radiators here, which has a contact with the air outside. So you have here a lot of slices here. So these slices here represent the radiator in order to dissipate this heat outside of the transformer. So this is natural. We don't have any kind of forced air or fans here. So the oil will be cooled due to dissipating this heat through the slices of this heat sink, and will return back again to the bottom of the transformer to continue cooling our transformer. Okay, so this is the shape of the oil natural air natural circulation of a transformer. We have also oil natural air forced. So oil natural means we don't have any kind of forced oil. So the oil is still work with the same function. However, instead of having just radiator in free space, we have radiators along with forced air. So we have fans to force the air to dissipate or transfer the heat from the hot oil. So this is the way, guys, in the oil natural air forced. So in oil natural air forced cooling, the heat generated by the core and windings of the transformer is transferred to the tank's walls and the radiators through the natural circulation of the oil. So until this point, it's the same as the oil natural air natural. But the forced air is directed over the transformer's cooling elements, tank radiator tubes. This cooling method is suitable for large transformers up to 60 megavolt ampere. So we can say from 15 or higher to 60 megavolt ampere, we can use this type of cooling, oil natural air forced. A third type, which is oil forced air forced. The heated oil is circulated from the top to the transformer tank to the heat exchanger. So here we have heat exchanger, and the air is forced through the heat exchanger by turning on a fan. Then the cool oil is returned to the bottom of the transformer tank. So in this case, guys, we have like forced circulation for our oil, okay, through a heat exchanger. So this is preferred, guys, with transformer less than 100 megavolt ampere. Okay, so this is air for oil forced air forced. If air is not sufficient, so the next step is going to be water. So the heated oil is circulated from the top of the transformer tank to the heat exchanger wall, where the pressurized water is used to separate the heat from the oil. So the idea is in the heat exchanger itself, guys, for sure we have, this is the forced oil. So this is the pump used for the forced oil, okay, and the tube to go to the heat exchanger. But here the heat exchanger, instead of having air like the previous method, we have here water. So inside the heat exchanger itself, we will have the radiator itself will have water tubes. And these water tubes, guys, are taking the hot water outside, and it has another way of cooling, okay, to dissipate the heat of the water and then return the cold water again. And here, guys, for this type, we may have a closed cycle or open cycle. So the open cycle water, this needs like having a source of water all of the time. But the closed cycle water, and this is the preferred one, you have to have a way to make cooling for the water inside these tubes, okay? But the water cycle is not clear in this figure right now, but you need just to know that the water inlet is coming from here, and the water outlet is from here, and the inlet or entered water is cold water, and the out water is the hot water because it gain the heat exchanged from the oil inside this heat exchanger. Okay, so these guys are the different types of cooling systems we have for our transformers. So this is what we have for the transformer cooling and the transformer constructions in three phase. So we covered most of the important material that you may find in industry. And again, guys, for sure, when you start working in such substations or transformers companies, you will have a detailed training for all topics you have for the transformer. So again, the class is nothing but giving you the basics that will allow you to start working in these technologies, and the detailed information and detailed design and consideration, you will learn that in the trainings in these companies that produce this technology. Thank you so much, guys. By these guys, we finish the transformer topics. In the next session, we will start in the DC motors topics. Thank you so much and have a nice weekend.